Tonight, we're going to talk about how many stars exist in the universe. Our own galaxy holds somewhere around 250 billion stars, packed into a single spiral disk 100,000 light-years across. And the Milky Way is just one galaxy. The universe holds trillions of them, most looking nothing like our own, smaller, fainter, some barely detectable even with our best instruments, each one carrying its own hidden population of stars that current telescopes are only just beginning to find. Layer all of that together, and the total climbs into a number so large, it becomes one of the hardest figures in all of science to actually pin down. By the end of tonight, you're going to understand exactly how big that number really is and how it gets built, piece by piece, from galaxy after galaxy. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Go outside tonight. Find a place away from city lights. Let your eyes adjust for 20 minutes. On a perfect night, from a perfect dark site, you will see approximately 5,000 stars. 5,000. That is the sum total of individual stars visible to human eyes anywhere on Earth, at any time, under any conditions. Out of everything that's up there, the human eye can see 5,000. That number will mean something different to you by the end of tonight. Let's start with the first problem, which is that you can't count stars the way you count apples in a bowl. You can't point at each one and say 1, 2, 3, working your way through the universe until you're done. The distances are too vast. Most stars are invisible to us, not because they don't exist, but because they're too far away, or hidden behind clouds of gas and dust, or simply too dim to detect, even with the best telescopes we've ever built. So astronomers do something clever. They count a small sample of stars in a region they can see clearly, figure out how many stars per unit of volume that represents, then multiply by the estimated volume of the galaxy or the observable universe, depending on what they're trying to calculate. This is inference, not counting. It's the same method a fisheries biologist uses to estimate how many fish are in a lake. You don't drain the lake and count them. You sample a section, count what you find, and extrapolate. The result is always an estimate. But it's a rigorous one, built on measurements, cross-checked against multiple methods, and revised every time better instruments come online. We're going to work through that estimate, piece by piece, and by the time we're done, you'll have a real number. Let's start with our own galaxy, the Milky Way. We live inside it, which creates an immediate problem. It's very hard to map something when you're embedded in it. Imagine trying to describe the layout of a city while you're standing in the middle of a single building. You'd need to figure out not just what you can see, but what's behind the walls and how the walls relate to everything else you can't see from where you're standing. That's our situation with the Milky Way. We're located about 26,000 light-years from the galactic center, orbiting in a spiral arm called the Orion Arm or the Local Arm, depending on which survey you're reading. We're not at the center. We're not at the edge. We're somewhere in the middle, and we've never seen our own galaxy from the outside. Every image you've ever seen of the Milky Way as a complete galaxy is either an artist's reconstruction or a photo of a different galaxy entirely. We know what the Milky Way looks like, mainly through indirect evidence. The way stars and gas are distributed, the velocities of objects orbiting the center. Infrared surveys that can see through the dust clouds, blocking our view in visible light. Radio observations that map the distribution of hydrogen gas. That radio technique deserves a closer look, because it's one of the strangest and most useful tools in this entire process. Neutral hydrogen atoms, the raw material that eventually collapses to form new stars, emit a very faint radio signal at a wavelength of about 21 centimeters, produced by a tiny quantum flip in the atom's electron. Any single atom only does this once every few million years, an almost negligible event. But interstellar space contains so much hydrogen that the combined signal from billions of atoms doing this simultaneously across the galaxy becomes clearly detectable from Earth. Radio telescopes map this 21-centimeter signal across the sky, tracing the location, motion, and density of hydrogen gas throughout the Milky Way, including regions completely hidden from visible light by dust. This mapping is how astronomers first revealed the Milky Way's spiral structure, since the gas traces out the same spiral arms where new stars are actively forming. It's also how astronomers estimate how much raw material remains available for future star formation, gas that hasn't yet collapsed, but eventually will. From all of this, we've pieced together a picture. The Milky Way is a barred, spiral galaxy. It has a central bar of stars, from which 2 or 4 main spiral arms extend outward. The disk of the galaxy is roughly 100,000 light-years across and about 1,000 light-years thick. Surrounding the disk is a much larger spherical halo of older, less luminous stars and enormous amounts of dark matter. Now, how many stars are in the Milky Way? For most of the 20th century, the standard estimate was around 100 billion. That number appeared in textbooks, in magazine articles, in television documentaries. 100 billion stars. The Milky Way. Then, infrared astronomy improved, and the number went up. Surveys using infrared light, which can penetrate the dust clouds that block visible light, revealed that the inner regions of the galaxy contain far more stars than we'd been able to see. Red dwarf stars in particular, which are dim in visible light but bright in infrared, turned out to be far more numerous than previous estimates had accounted for. The revised estimate for the Milky Way is somewhere between 200 billion and 400 billion stars. Maybe more. The uncertainty isn't a failure of astronomy. It's an honest acknowledgement of how difficult it is to count objects spread across a disk 100,000 light-years wide when you're standing inside it. For the purposes of tonight, let's use 250 billion as a working estimate for the Milky Way. That's the rough center of the range most current surveys agree on. 250 billion stars, just in our galaxy. Before we move beyond the Milky Way, we need to understand something that completely changes the arithmetic. Something that wasn't fully appreciated until the middle of the 20th century. Red dwarfs. Red dwarf stars are the most common type of star in the universe, by a very large margin. They make up somewhere between 70 and 80% of all stars in the Milky Way. You would think that means they dominate our picture of the night sky. They don't. You can't see a single red dwarf with the naked eye from Earth. Not one. The nearest star to our solar system is Proxima Centauri. It's a red dwarf. It's 4.24 light-years away. Under ideal conditions, a healthy human eye can see stars down to about magnitude 6. Proxima Centauri's apparent magnitude is 11. It's about 100 times too dim to see, even though it's literally the closest star to the Sun. Red dwarfs are tiny. They're cool. Their surface temperatures run between roughly 2,100 degrees Celsius and 3,400 degrees Celsius, or about 3,800 degrees Fahrenheit to 6,200 degrees Fahrenheit. Compare that to the Sun's surface, close to 5,400 degrees Celsius, or nearly 10,000 degrees Fahrenheit. They emit mostly red and infrared light, rather than the yellow-white light we see from the Sun, and they're small. The smallest red dwarfs are barely larger than Jupiter. A red dwarf, with 8% of the Sun's mass, sits right at the boundary between star and not a star. Below that threshold, nuclear fusion doesn't ignite, and you have a brown dwarf instead. But here's what matters for counting. Red dwarfs are not just common. They are astronomically common in the most literal sense of that phrase. The Milky Way contains an estimated 160 to 200 billion red dwarf stars. Out of a total of 250 billion stars, that means roughly 3 out of every 4 stars in our galaxy is a red dwarf you will never see with your own eyes. This matters enormously when we start counting the stars in other galaxies, because different types of galaxies have different ratios of red dwarfs to other kinds of stars, and those ratios have large effects on the final number. There's another reason direct counting fails, and it has nothing to do with distance. It's called crowding. In the densest parts of the Milky Way, especially near the galactic center, stars are packed so tightly that individual telescopes can't tell them apart. Instead of seeing thousands of separate points of light, an instrument sees one smeared blur, overlapping starlight that no amount of processing can fully separate back into individual stars. Astronomers call this the confusion limit. Past a certain density, you stop counting stars one by one and start measuring total brightness instead, then dividing by an assumed average brightness per star to estimate how many stars must be contributing to the glow. The core of the Milky Way, within just a few dozen light-years of the center, may contain millions of stars packed into a volume where our own stellar neighborhood holds only a handful. Globular clusters have the same problem on a smaller scale. These are tight, spherical swarms of ancient stars, some containing 1 million stars inside a region only a few dozen light-years across. Near the center of a dense globular cluster, stars are packed close enough that they sometimes collide, something that essentially never happens in the quiet outskirts of a galaxy like ours. Every one of these crowded environments makes direct counting impossible, which forces astronomers back onto the same statistical method used to estimate the total star count of the entire universe. The difficulty of counting stars isn't only about vast distance. It's built into the physical structure of galaxies themselves, even in the parts relatively close to home. The next piece of the count is galaxies. Because the total number of stars in the universe depends first on how many galaxies exist, and then on how many stars are in each galaxy. For much of the 20th century, astronomers estimated there were around 100 billion galaxies in the observable universe. That number came from extrapolating the galaxy counts in the Hubble Deep Field images. In December of 1995, the Hubble Space Telescope did something that sounds almost reckless. Astronomers pointed it at a tiny patch of sky in the constellation Ursa Major, a patch so small that if you held a grain of sand at arm's length, the grain would cover it. The patch appeared completely empty to ground-based telescopes, so Hubble stared at it for 10 consecutive days. 100 hours of exposure time, gathering every photon it could detect. When the image came back, astronomers found themselves looking at approximately 3,000 galaxies. 3,000 galaxies in a region of sky that appeared completely dark. That was the Hubble Deep Field. Later, astronomers did the same exercise in the southern hemisphere. Same result. 3,000 galaxies in an empty-looking patch. Extrapolating those numbers across the whole sky gave an estimate of somewhere around 50 billion to 100 billion galaxies in the observable universe. For 20 years, that number held. Then, in 2016, a team led by astronomer Christopher Consolis at the University of Nottingham published a paper that revised that estimate upward. In a single paper, that estimate was revised upward by a factor of 10 to 2 trillion galaxies. The reason why changes how you think about everything we'd assumed we understood about the observable universe. The previous estimates had only counted galaxies bright enough for Hubble to detect. But Consolis and his team used mathematical modeling to account for the galaxies that were too small, too faint, or too far away to be directly observed. Most galaxies in the early universe were small, diffuse structures that have long since merged into larger galaxies or simply faded beyond detection. When you account for all the galaxies that existed at every stage of cosmic history, including the ones we can't directly see, the number rises dramatically. 2 trillion galaxies in the observable universe. That's the current, best estimate. Not all of them still exist in their original form. Many have merged with other galaxies over cosmic time. But 2 trillion is the count of distinct galactic structures that have existed within the volume we can observe. 2 trillion is a number that resists comprehension. If you counted one galaxy per second without stopping, you would need 63,000 years to finish. Counting galaxies has its own version of the red dwarf problem, and it comes from the opposite direction. Objects that are far too bright rather than far too dim. Quasars are among the most luminous objects in the universe, powered not by stars, but by supermassive black holes, actively feeding on infalling gas at the centers of distant galaxies. A single quasar can outshine every star in its host galaxy combined, sometimes by a factor of 1,000 or more, which means that from enormous distances, a quasar can look like a single, unusually bright star rather than the galaxy actually surrounding it. Early galaxy surveys occasionally misclassified quasars as foreground stars within our own galaxy, simply because a single brilliant point of light is hard to distinguish from a much fainter, much closer star without detailed spectroscopy. Sort that error out incorrectly in either direction, and it throws off both the star count and the galaxy count at the same time. Modern surveys catch this by analyzing the light spectrum rather than relying on brightness and position alone, since a quasar's light carries a very specific red-shifted signature that a nearby star simply doesn't have. But the correction only works because astronomers know to look for it. A reminder that every category used tonight, star, galaxy, quasar, cluster, depends on increasingly sophisticated ways of telling very different objects apart at distances where they all just look like points of light. Now, galaxies are not all alike. This matters because the number of stars per galaxy varies enormously. The Milky Way is a medium to large spiral galaxy with 250 billion stars. But there are galaxies that dwarf it completely. IC 1101 is the largest galaxy we've ever found. It's an elliptical galaxy located about 1 billion light-years from Earth in the constellation Virgo, near the Serpens border. It's roughly 500,000 light-years across. Using the isophotal measurements astronomers consider most reliable, some older, more popular figures cite a diameter in the millions of light-years. But those numbers include an extremely diffuse outer halo. Most astronomers don't count as part of the galaxy itself. The Milky Way is 100,000 light-years across. IC 1101 is about 5 times wider. Its volume, relative to the Milky Way, is mind-bending. Estimates of its stellar population run to 100 trillion stars, 400 times more than the Milky Way, all inside a single galaxy. Then there are dwarf galaxies, which represent the other extreme. The Canis Major dwarf is among the nearest such structures to the Milky Way, though whether it's a genuine separate galaxy or simply a feature of the Milky Way's own warped, flared outer disk is still debated among astronomers. It contains about 1 billion stars, roughly 1/250th of the Milky Way's stellar population. The Segway, 2 dwarf spheroidal galaxy, one of the smallest known galaxies, contains fewer than 1,000 stars. Not 1,000 billion. 1,000. The universe contains galaxies spanning 11 orders of magnitude in stellar population, from fewer than 1,000 stars to more than 100 trillion. When you're trying to estimate the total number of stars in the observable universe, which type of galaxy you assign as average matters enormously. This is where the estimate gets complicated and where different astronomers arrive at different numbers. A galaxy-by-galaxy average, weighted by how many galaxies of each type exist, lands on something like 100 billion stars per galaxy. That's the number most often used in popular science writing. It's a convenient figure. It's also probably an underestimate, because it doesn't fully account for the abundance of red dwarfs in elliptical galaxies. More on that in a moment. It's worth explaining exactly where that 100 billion stars per galaxy figure actually comes from, because it isn't guesswork. Astronomers measure a galaxy's total light output, its luminosity, using telescopes calibrated with extreme precision. Then they estimate the galaxy's total mass, using the motion of its stars and gas, or the way its gravity bends light from objects behind it, a technique called gravitational lensing. Divide mass by light, and you get something called a mass-to-light ratio, a single number that describes, on average, how much material it takes to produce a given amount of brightness in that particular galaxy. That ratio is different for every type of galaxy, because it depends heavily on what kind of stars dominate the mix. A galaxy full of young, massive blue stars produces enormous light for relatively little mass, since a handful of hot giants can outshine millions of fainter stars combined. A galaxy full of old red dwarfs does the opposite, containing enormous mass, and therefore enormous numbers of stars, while producing comparatively little light. This is exactly the trap that caught astronomers off guard with elliptical galaxies, and exactly what Peter van Dokkum's spectral analysis was designed to correct. Once you have a reliable mass-to-light ratio for a given galaxy type, and a reasonable assumption about the average mass of an individual star, you can divide the galaxy's total stellar mass by that average and arrive at an estimated star count, without ever counting a single individual star directly. This is the actual machinery behind every galaxy averaged figure quoted tonight. Not a guess, and not a direct tally, but a chain of measurements, mass, light, and an assumed stellar population, stacked together into a number precise enough to trust and uncertain enough to keep revising. The basic calculation multiplies 2 trillion galaxies by roughly 100 billion stars per galaxy on average, which gives you 200 sextillion, a 2 followed by 23 zeros. That is the standard estimate for the number of stars in the observable universe. You'll see this number reported as roughly 10 to the 23rd power in scientific papers. You'll also see it reported as 200 billion trillion, because a sextillion is a billion trillion. Let's try to get a sense of the scale. If you took 200 sextillion grains of sand, they would fill a sphere only about 18 miles across, nowhere close to the size of a planet. If you lined up 200 sextillion hydrogen atoms in a row, the line would stretch about 13 billion miles, roughly 140 times the distance from the Earth to the Sun. A long way, but still far short of a single light year. If every person alive on Earth right now were assigned stars to count, each person at 1 star per second, counting continuously without sleep, it would take the entire human population close to 800,000 years to count them all. 200 sextillion. That's the number. But the number comes with a significant caveat. It might be wrong. Not because the method is flawed, but because what we mean by average stars per galaxy depends heavily on what we assume about the proportion of red dwarfs. In 2010, a team of astronomers led by Peter van Dokkum at Yale University published a paper with uncomfortable implications for anyone who liked the neat round number of 200 sextillion. Van Dokkum and his colleague Charlie Conroy were studying elliptical galaxies. Elliptical galaxies are the large, roughly spherical or egg-shaped galaxies that form when spiral galaxies collide and merge. They're extremely common. They're also very old, containing mostly ancient, dim stars rather than the bright young stars you see in spiral galaxies. Van Dokkum and Conroy were studying the spectra of these elliptical galaxies, looking specifically for absorption features caused by red dwarf stars. Red dwarfs leave faint but distinctive fingerprints in the light of a galaxy. By measuring how strong those fingerprints are, you can infer how many red dwarfs the galaxy contains. What they found contradicted previous assumptions. Elliptical galaxies appeared to contain far more red dwarfs relative to other types of stars than the Milky Way does. Up to 3 times more per unit of stellar mass. This was unexpected. Most estimates of stellar populations in elliptical galaxies had been made by assuming that ellipticals have roughly the same ratio of stellar types as the Milky Way. Van Dokkum and Conroy's data suggested that assumption was wrong. If elliptical galaxies, which represent a large fraction of all the stellar mass in the universe, contain 3 times as many red dwarfs as previously thought, the total star count goes up significantly. The revised estimate, accounting for an elliptical galaxy-heavy red dwarf population, pushes the total towards 600 sextillion or more, 3 times the standard number. This is an active area of research. Not all astronomers agree on the magnitude of the effect. The techniques for inferring red dwarf populations from galaxy spectra are still being refined. But the basic direction is clear. If anything, 200 sextillion is probably a lower bound, not a final answer. The true number may be considerably higher. The assumption Van Dokkum's work challenged has a formal name. The initial mass function. It's a mathematical description of how many stars of each mass are produced whenever a cloud of gas collapses to form a new stellar population. And it's one of the most load-bearing assumptions in all of astrophysics. The modern version traces back to astronomer Edwin Salpeter, who in 1955 proposed a simple mathematical relationship. Low-mass stars vastly outnumber high-mass stars, following a specific, predictable curve. For decades, astronomers treated the Salpeter function and its later refinements as roughly universal, assuming the same ratio of small stars to large stars applied everywhere, in every galaxy, regardless of type. That assumption is precisely what Van Dokkum's spectroscopy called into question. If elliptical galaxies genuinely produce a bottom-heavier mix, more red dwarfs relative to Sun-like and massive stars than spiral galaxies like the Milky Way, then a single universal initial mass function was never accurate to begin with. Every galaxy might have its own recipe, shaped by the specific density, temperature, and turbulence of the gas cloud it formed from. This is still being worked out. But it explains why the star count carries the uncertainty it does. It isn't a rounding error in a well-understood system. It's a genuine unresolved question about how star formation actually works, sitting underneath every galaxy average number in this entire calculation. Let's step back and make sure the scale is landing. The observable universe is a sphere about 93 billion light-years in diameter. The Sun is about 865,000 miles in diameter. A light-year is about 5.9 trillion miles. The observable universe is so large that if you shrank it down to the width of the continental United States, the Milky Way would be about the length of a car. We are unimaginably small. And yet, within that unimaginable volume, there are a minimum of 200 sextillion suns. Most of them are red dwarfs. Most of them are burning right now, fusing hydrogen into helium in their cores, maintaining the balance between gravity and radiation pressure that defines what it means to be a star. Most of them will continue burning for longer than the universe has currently existed. Red dwarfs can live for 1 trillion years or more. The universe is 13.8 billion years old. Red dwarfs, born in the early universe, are still teenagers. They have roughly 70 times more life ahead of them than behind. There are also stars that exist outside of galaxies entirely. These are the intracluster stars, or intergalactic stars, sometimes called rogue stars or orphan stars. They're stars that have been ejected from their parent galaxies through gravitational interactions, galaxy mergers, or close encounters with supermassive black holes. In the Virgo cluster, the nearest large galaxy cluster to our local group, astronomers estimate that between 10 and 50% of all stars are not inside any galaxy. They're drifting through the space between galaxies, not bound to any galactic structure, invisible in surveys that only look at identified galaxies. In galaxy clusters, where mergers and gravitational interactions are common, these intracluster stellar populations can be enormous. Some studies suggest that the intracluster stars in a cluster like Virgo could rival or exceed the total stellar population of all the cluster's galaxies combined. If that holds across the universe, the 200 sextillion estimate is missing a significant fraction of all stars. We can't count what we can't see. And intracluster stars are extraordinarily difficult to observe directly. They produce a faint, diffuse glow of light spread across enormous volumes of space, rather than a bright, concentrated source that stands out against the darkness. Now, let's talk about time. Because the question, how many stars exist in the universe, has a hidden complication. When you say, exist right now, what do you mean? Light has a finite speed. The sun is 8 light minutes away. When you look at it, you see it as it was 8 minutes ago. Proxima Centauri is 4.24 light years away. You're seeing it as it was 4 years ago. Andromeda is 2.5 million light years away. The light entering your eye from Andromeda tonight left that galaxy when our ancestors were using stone tools for the first time. The most distant galaxies we can observe are over 46 billion light years away. The light we see from them left when the universe was only a few 100 million years old. We're not looking at those galaxies as they are. We're looking at them as they were. Some of those distant galaxies no longer exist in their original form. They've merged with other galaxies. Their stars have evolved and died. The universe we observe through our telescopes is a composite image spanning nearly 14 billion years of cosmic history, all presented to us simultaneously because the light from different epochs is arriving at our location at different times. When we say the observable universe contains 200 sextillion stars, we're really saying something more like, when we integrate over all the light reaching us from all distances, accounting for the different epochs represented by those different distances, the total implied stellar population is approximately 200 sextillion. It's not a snapshot of the universe right now. It can't be. No such snapshot is possible. The universe is so large that right now doesn't have a meaning across cosmic distances in the way it does in everyday life. Let's talk about what a star actually is. Because 200 sextillion is a count of individual things, and it's worth understanding exactly what those things are. A star is a nuclear reactor held together by gravity. That's the clearest definition. It's a ball of mostly hydrogen and helium gas compressed by its own gravity to such extreme temperatures and pressures at the center that hydrogen nuclei fuse together to form helium, releasing energy in the process. That energy is what makes stars shine. The energy comes from E equals mc squared. When 4 hydrogen nuclei fuse into one helium nucleus, the resulting helium nucleus is slightly less massive than the 4 original hydrogens. That missing mass is converted directly into energy. The conversion rate is extraordinarily efficient. The sun converts about 600 million tons of hydrogen into helium every second. In doing so, it loses about 4 million tons of mass per second. That 4 million tons of mass becomes energy. And that energy radiates outward as the light and heat you feel on your face on a summer day. The sun has been doing this for 4.6 billion years. It will continue doing it for another 5 billion years. At the end, it will have converted only about 0.1% of its original mass into energy. it has an enormous amount of fuel left. But the Sun is not representative of the universe's stars. It's a medium-sized star of a type called G-type, or yellow dwarf. The vast majority of stars are smaller, and a small number are vastly larger. Astronomers classify stars by their spectral type, using the letters O, B, A, F, G, K, and M. The sequence runs from hottest to coolest. That specific, seemingly arbitrary sequence of letters has a human history behind it. It was largely the work of Annie Jump Cannon, an astronomer at Harvard College Observatory in the early 20th century, working alongside the same team that included Henrietta Swan Leavitt. Cannon personally classified the spectra of more than 350,000 stars by eye, examining photographic plates one at a time and sorting each star into its proper category based on the pattern of dark lines in its light. Her system simplified an earlier, more cluttered classification scheme down to the clean O, B, A, F, G, K, M sequence, still used today, ordered by temperature rather than the historical order in which the categories happen to be discovered. Generations of astronomy students have used the mnemonic "Oh, be a fine girl, kiss me to remember the order," a strange piece of trivia riding on top of a system built from 350,000 individually inspected stars. O stars are blue giants and supergiants, burning at surface temperatures above roughly 29,700 degrees Celsius, or about 53,500 degrees Fahrenheit. They're among the most luminous objects in the universe. A single O star can outshine the Sun by a factor of 1,000,000 or more. They're rare, violent, and short-lived. An O star might burn for only a few million years before exploding as a supernova. B stars are blue to blue-white, somewhat cooler than O stars, but still extraordinarily bright. Rigel, the bright blue star in Orion's foot, is a B star. It shines with the luminosity of approximately 120,000 suns. A stars are the white and white-blue stars at the upper middle of the stellar sequence. Sirius, the brightest star in the night sky, is an A star. Sirius is 25 times more luminous than the Sun. F stars are yellow-white, slightly hotter and more massive than the Sun. G stars are yellow. The Sun is a G star. Tau Ceti, one of the nearest stars with a roughly Earth-like planet in its habitable zone, is also a G star. K stars are orange, slightly cooler and smaller than the Sun. Alpha Centauri b is a K star. And then there are M stars, red dwarfs, the most common type of star in the universe. Surface temperatures between roughly 2,100 degrees Celsius and 3,400 degrees Celsius, or 3,800 degrees Fahrenheit to 6,200 degrees Fahrenheit. Between 70 and 80% of all stars, the ones you can never see with the naked eye. Below M stars sits the boundary between star and brown dwarf at about 80 Jupiter masses, or 8% of a solar mass. Below that threshold, gravity alone cannot compress the core enough to sustain hydrogen fusion. The object glows for a while from gravitational contraction, then slowly fades. These brown dwarfs are an astronomical grey area, more than planets, less than stars. No one is quite sure how many of them exist. Their faintness makes them hard to detect. They may rival or even outnumber true stars in some counts. Their existence is one of many reminders that the universe doesn't care about the categories we've invented to describe it. The spectral sequence describes temperature and color, but it doesn't capture just how extreme the size range of stars actually is. On the small end, red dwarfs can be barely larger than Jupiter, a star you could theoretically fit dozens of into the volume of the Sun. On the large end, the universe contains stars so big that the word star barely feels adequate. The current record holder is a red hypergiant known as Stephenson 218, located in the constellation Scutum. Its radius is estimated at roughly 930 million miles, meaning that if it replaced the Sun at the center of our solar system, its surface would extend out past the orbit of Saturn. Mercury, Venus, Earth, Mars, Jupiter, all of it would be inside the star. Despite that almost incomprehensible size, Stephenson 218 is far less massive than its volume suggests. Because red hypergiants are extremely diffuse, their outer layers barely held together by gravity at all. Stars like this live fast and end quickly, burning through their fuel in a few million years, a blink of an eye compared to the trillion-year lifespans of the red dwarfs that make up most of the universe's stellar population. The stars that dominate the count, by sheer numbers, are small, dim, and almost eternal. The stars that dominate our imagination, the giants and hypergiants, are rare, brief, and represent only the smallest fraction of everything actually out there. Before going further out, look at what's actually nearby. Because all these classifications become much more concrete when you look at the stars closest to us. Within 10 light-years of the Sun, there are about 25 known individual stars grouped into roughly 14 separate systems. Alpha Centauri is the closest system, a group of 3 stars 4 light-years away. 2 of them, Alpha Centauri A and Alpha Centauri B, are Sun-like stars orbiting each other. The third is Proxima Centauri, the red dwarf already mentioned, orbiting the other 2 from much farther out. Barnard's star comes next, about 6 light-years away, a lone red dwarf famous for having the fastest apparent motion across our sky of any known star. Wolf 359 sits at roughly 7.9 light-years, another faint red dwarf. Sirius, the brightest star in Earth's night sky, is 8.6 light-years away, and it's actually a binary system, a bright A-type star paired with a small, dense, white dwarf. Most of the stars in this nearby census are red dwarfs. Only Sirius and Alpha Centauri A and B are bright enough to see without a telescope. The rest sit below naked eye visibility, even though they're our literal closest neighbors, a small-scale preview of the pattern that holds across the entire universe. Expand the search radius, and the numbers climb fast. Within 20 light-years, there are roughly 70 known star systems. Within 100 light-years, the count climbs into the tens of thousands. And this is still an infinitesimal fraction of the galaxy. The galactic center is about 26,000 light-years away. The far edge of the Milky Way's disk is more than 60,000 light-years out. Everything visible to the naked eye, every star in every constellation, sits inside a tiny bubble a few thousand light-years across. A rounding error compared to the galaxy it's embedded in. Now, let's talk about how stars actually come to exist. Because the number 200 sextillion didn't appear all at once. Stars have been forming throughout cosmic history at rates that have changed dramatically over time. The first stars in the universe formed when the universe was only about 100 to 200 million years old. These stars are called population 3 stars. They formed from clouds of primordial gas that was almost entirely hydrogen and helium. No carbon, no oxygen, no iron, no heavy elements at all. Because those elements didn't exist yet. They had to be made. Population. 3 stars were likely very massive, hundreds of times more massive than the Sun, in many cases. The reason is related to the absence of heavy elements. When modern stars form in molecular clouds, the cooling of the cloud is partly driven by complex molecules and dust grains made of heavy elements. These cooling mechanisms allow the cloud to fragment into smaller pieces before collapsing, producing smaller, lower-mass stars. Without heavy elements, the primordial gas clouds couldn't cool as efficiently. They tended to collapse into larger, hotter, more massive stars. These population 3 stars lived fast. The most massive burned through their fuel in just a few million years and exploded as supernovae, or possibly as direct collapse black holes. Their explosions seeded the surrounding gas with the first heavy elements: carbon, oxygen, nitrogen, silicon, iron. Elements that hadn't existed before, mixed into the gas, available for the next generation. For decades, this early picture of population 3 stars was theoretical. Nobody had actually observed a genuine population 3 star, or the earliest galaxies they would have formed inside. That started to change with the James Webb Space Telescope, launched in December of 2021 and fully operational the following year. Webb was built specifically to see farther back in time than Hubble ever could, using infrared instruments sensitive enough to catch the faint, stretched light of the very first galaxies. And almost immediately, it found something unexpected. Galaxies that appeared to be already large, already structured, and already surprisingly bright, at distances corresponding to just a few 100 million years after the Big Bang. That timing was a problem. The standard models of galaxy formation didn't predict galaxies that massive forming that quickly. There hadn't been enough time, according to the existing theory, for that much gas to collapse and that many stars to form. Astronomers are still working through what this means. Some of it may be observational, galaxies appearing brighter than expected because of how efficiently their young, massive stars convert gas into light. Some of it may point to gaps in the standard model of early star formation, meaning the first generation of stars formed faster, or in larger numbers, or under different conditions than previously assumed. Either way, the practical effect on the star count is the same direction it's always been. Every time a better instrument looks farther back, the number of stars implied by the early universe goes up, not down. The 200 sextillion figure already tries to account for this, using models calibrated against the best available data. But Webb is actively rewriting that data, one deep field at a time, and the total is likely to move again as more of its observations are analyzed. The next generation of stars is called Population 2, formed from gas that now contained a small but meaningful fraction of heavy elements, courtesy of the Population 3 supernovae. Population: 2 stars are old. They formed over 10 billion years ago in the early universe. Many are still alive today because they tend to be low-mass, low-luminosity stars that burn slowly. The globular clusters you see orbiting the Milky Way are packed with Population 2 stars. Tight, spherical balls of hundreds of thousands of ancient stars orbiting the galactic center in elliptical orbits, remnants of the early universe preserved in the halos of galaxies. Population: 2 stars are metal-poor in astronomical terminology. When astronomers say metals, they mean all elements heavier than hydrogen and helium. Every carbon atom in your body, every oxygen atom in your lungs, every calcium atom in your bones. To an astronomer, all of those are metals. Population 2. Stars have less of them than the Sun does because they formed from gas that had only been enriched once by Population 3 supernovae. Methuselah's star is a Population 2 star, formally designated HD 140283. It's about 200 light-years from Earth. Its age has been estimated at approximately 12 billion years, based on the most recent analysis of the star. Earlier estimates had placed it as old as 14.5 billion years, which would have made it older than the universe itself, an impossibility that took years of refined distance and composition measurements to resolve. Methuselah's star may be one of the oldest individual stars still in existence. It formed when the universe was very young, from some of the first chemically enriched gas to exist anywhere in the cosmos. It has been burning ever since, quietly, for roughly 12 billion years. The Sun is 4.6 billion years old. Methuselah's star has been burning for over 2.5 times longer than the Sun has existed. Population 1. Stars are the youngest generation. They formed from gas that had been enriched by multiple generations of stellar evolution and supernova explosions. They're metal-rich. The Sun is a Population 1 star. So is every star you can see with your naked eye in the night sky, with very few exceptions. Population 1 stars are found predominantly in the disk and spiral arms of galaxies, where active star formation is ongoing. The interstellar medium in those regions has been continuously enriched by the cycle of star formation, stellar evolution, and stellar death. Stars form, burn through their fuel, and when they go, they return most of their mass to the interstellar medium, enriched with the heavy elements forged in their cores, and the next generation forms from that material. 13.8 billion years of this cycle has produced stars with increasingly complex compositions. The Sun contains more than 90 naturally occurring elements. That diversity of elements is a direct result of billions of years of stellar nucleosynthesis. You are made of the waste products of dead stars. Every atom in your body, heavier than helium, was forged in the core of a star that no longer exists. The calcium in your bones was synthesized in a supernova shockwave. The iron in your blood was made in the dying core of a massive star. The oxygen in the air you're breathing right now was created in the interior of a star that exploded before our solar system was born. This isn't metaphor. It's nuclear physics. The universe spent 10 billion years building heavy elements before our solar system formed. The stars that died to make those elements are long gone, but their cores are still here. We breathe them. There's a definitional wrinkle buried inside all of this counting. What actually counts as one star? Most people picture a star the way the sun looks, a single point of light, alone in space. But the sun is unusual in that respect. A large fraction of all stars are not alone. They exist in binary systems, two stars orbiting a shared center of mass, or in triple systems, or occasionally in even larger groupings. Among sun-like stars, roughly half exist in binary or multiple systems. Among the most massive stars, the fraction is even higher, with some studies suggesting the majority of O and B stars have at least one companion. Red dwarfs, despite being the most numerous stars in the universe, tend to be single more often than not, though a meaningful fraction still have companions. This matters for the star count, because every galaxy survey and every stellar census has to make a choice. Do you count a binary system as one object or two? Standard practice counts individual stars, not systems, which means the 200 sextillion figure already reflects binaries as separate entries. But it also means that some of the brightest points of light in any given galaxy survey aren't single stars at all. They're two stars so close together that their light blends into what looks, from enormous distances, like a single source. Sirius is a nearby example. For most of human history, it appeared to be one star. It took careful 19th century observations of tiny wobbles in its motion to reveal a hidden companion, a white dwarf now known as Sirius B, orbiting so close and so faint that it remained invisible until astronomers went looking for exactly this kind of gravitational fingerprint. If a star that close to Earth kept a companion hidden for centuries, it raises an obvious question about how many similarly close pairs exist among the stars too distant to resolve at all. Binary and multiple systems also interact in ways single stars never do. Close binaries can transfer mass from one star to the other, reshaping both of their evolutionary paths, sometimes reigniting a star that should have already faded, sometimes feeding a companion until it detonates as a supernova far earlier than it otherwise would have. None of this changes the total count dramatically, but it's a reminder that even the definition of a single star, the basic unit being counted across 200 sextillion instances, isn't always as clean as it sounds. Star formation in the universe has not been constant. It peaked. About 10 billion years ago, when the universe was roughly 3 to 4 billion years old, star formation was running at its maximum rate. New stars were being born across the universe at a pace roughly 10 times higher than today. The cosmic star formation rate has been declining ever since. Slowly at first, then more steeply. Today, the Milky Way forms perhaps 1 to 2 new stars per year. At peak formation rates, it may have been forming 20 or more. Put birth and death side by side, and the universe looks less like a fixed inventory and more like a slow, ongoing turnover. At the same time that new stars are quietly condensing out of collapsing gas clouds, older stars are constantly reaching the end of their lives. Most die quietly, swelling into red giants and shedding their outer layers to become white dwarfs, a slow fade rather than an event. A much smaller number die violently. Across the entire Milky Way, a supernova is thought to occur roughly once every 50 years on average, though none has been directly observed in our own galaxy since the invention of the telescope. Scale that up across the observable universe, and a supernova is going off somewhere out there several dozen times every single second. Every one of those explosions marks the permanent end of a massive star, and often the beginning of the elements that will form the next generation. None of this shifts the 200 sextillion total by much on any human timescale. The numbers being gained and lost are trivial compared to the total population, but it's a reminder that the figure quoted throughout tonight isn't frozen. It's a census of a population that is, at every single moment, quietly being added to and quietly being subtracted from across 2 trillion galaxies, all at once. The implication of this declining star formation rate is that the universe has already made most of the stars it's ever going to make. Roughly 90 to 95% of all the stars that will ever exist in this universe's lifetime have already formed. We're not at the beginning of the age of stars. We're past the peak. Astronomers call the period from about 2 billion to 4 billion years after the Big Bang the cosmic noon, when star formation was at its height and the universe was filled with young, hot, bright, actively evolving galaxies. That era is over. The universe is quieter now, still forming stars, still alive, but past its most productive period. The stars that will form in the future will mostly be low-mass red dwarfs, because those are the stars that form most easily from diffuse, metal-rich gas. The age of bright, massive blue stars is winding down. The universe's future belongs to the quiet, dim, long-lived red dwarfs. There's another layer to this problem that has nothing to do with distance or dimness or which galaxy a star happens to sit inside. It has to do with time. Not the time it takes light to reach us, but the time it takes a star to actually finish becoming a star. Star formation isn't instantaneous. It's a slow, messy, drawn-out process, and depending on exactly when you look, the thing you're looking at may not qualify as a star yet at all. The nearest active stellar nursery to Earth sits inside the Orion Molecular Cloud Complex, roughly 1,300 light-years away. Part of it is visible without a telescope, as the faint smudge below Orion's belt, known as the Orion Nebula. That smudge is a cloud of cold hydrogen gas and dust, tens of light-years across, and it is actively manufacturing new stars right now, tonight, while you're watching this. At its heart sits the Trapezium Cluster, 4 massive young stars whose combined radiation lights up the surrounding gas and carves it into the glowing shape astronomers first catalogued centuries ago. Those 4 stars are almost unimaginably young by stellar standards, somewhere between 100,000 and 1 million years old. Compare that to the Sun's 4.6 billion years. If the Sun's lifetime were scaled down to a single calendar year, the trapezium stars would have formed sometime in the last few hours of December 31st. They are, on any cosmic timescale, newborns. Surrounding them, scattered through the nebula, are hundreds of protostars in various stages of formation, And this is where the counting problem gets genuinely strange. A protostar isn't a fully formed star. It's a dense core of collapsing gas, pulled together by its own gravity, growing hotter and denser at the center as more material falls inward. It glows, faintly, from the heat of that gravitational collapse alone, radiating in the infrared long before any nuclear fusion begins. Surrounding it is often a rotating disk of leftover gas and dust, the same disk that may eventually flatten into planets. At this stage, there is no fusion happening. No hydrogen is being converted into helium. The object is bright only because it is falling in on itself, converting gravitational energy into heat. Astronomers call this a pre-main sequence phase, and it can last anywhere from a few 100,000 years to tens of millions of years, depending on the mass of the forming star. Lower mass protostars take longer to reach the point where their cores finally get hot and dense enough to ignite sustained fusion. Once fusion ignites and stays lit, the object settles onto what's called the main sequence, the long, stable, hydrogen-burning phase that defines almost the entire adult life of a star. That's the moment most definitions agree a protostar has become an actual star. But not every survey draws the line there. Some catalogs count anything with enough mass to eventually ignite fusion, regardless of whether it already has. Others only count objects that have visibly reached the main sequence, which means a young cluster like the trapezium region contains an uncertain number of borderline cases. Cores that are massive enough to become stars, glowing brightly enough to be detected, but not yet technically burning hydrogen. Depending on which definition a given study uses, the same nebula can produce different star counts from the same data. A related population makes this even messier. T Tauri stars are young, low-mass stars that have already ignited fusion, or are right on the edge of doing so, but haven't yet settled into a stable, predictable brightness. They flare, dim, and flicker unpredictably, still shedding the last of their formation-era turbulence, still often surrounded by the remnants of their birth disk. They're unambiguously stars by most definitions, but they don't behave like mature ones, and their instability makes them harder to catalogue consistently across large surveys. One of the most striking images ever produced of this process doesn't come from Orion at all. It comes from the Eagle Nebula, roughly 7,000 light-years away, in a structure that became famous under a different name entirely, the Pillars of Creation. Photographed first by Hubble in the 1990s, and again by Webb decades later. The pillars are towering columns of cold gas and dust, several light-years tall, each one riddled with small, dense knots called evaporating gaseous globules. Inside many of those knots, protostars are forming right now, hidden from visible light entirely, detectable only in infrared, where Webb's instruments can see straight through the obscuring dust to the collapsing cores inside. The pillars themselves are being slowly eroded by the intense radiation of nearby massive stars, sculpted into their famous shape by the very process of star formation happening around them. In a few 100,000 years, on a timescale short by galactic standards, the pillars may not exist at all, eaten away entirely. Their remaining gas either fed into forming stars or blasted outward by radiation and stellar winds. Star formation is also strikingly inefficient, and that inefficiency matters for the count. Molecular clouds, like the one in Orion, contain enormous reserves of gas, sometimes hundreds of thousands of times the mass of the Sun. But only a small fraction of that mass actually ends up locked inside new stars. Most estimates put the star formation efficiency of a typical molecular cloud somewhere between 1 and 10%. The rest of the gas gets dispersed, blown away by the radiation and stellar winds of the stars that do form, or simply never collapses far enough to ignite anything at all. This means that when astronomers try to estimate how many stars a given amount of interstellar gas will eventually produce across an entire galaxy, they aren't doing a simple mass conversion. They're applying an efficiency factor derived from studying nearby regions like Orion in extraordinary detail, then extrapolating that factor to clouds too distant and too faint to study directly, which folds yet another layer of inference into the 200 sextillion figure. There's a final piece of this that connects back to something closer to home. Stars rarely form alone. The overwhelming majority of stars, including almost certainly the Sun, formed as part of a cluster, a group of hundreds or thousands of siblings condensing out of the same collapsing cloud at roughly the same time. Open clusters like the Pleiades, visible to the naked eye as a tight knot of blue-white stars in the constellation Taurus, are relatively young examples of exactly this kind of birth group, still loosely bound together, still recognizable as a family. But most clusters don't stay together. The gravitational pull between individual stars in a cluster is weak compared to the tidal forces of the galaxy as a whole, and over tens or hundreds of millions of years, most open clusters slowly disperse, their members drifting apart, scattered across different spiral arms, eventually losing any trace of their shared origin. The Sun's birth cluster dispersed long ago. Somewhere out there, among the 250 billion stars of the Milky Way, are the Sun's actual stellar siblings, born from the same cloud at the same time, roughly 4.6 billion years ago. Astronomers have spent years trying to identify even one of them by matching chemical fingerprints in stellar spectra, since siblings born from the same cloud should share a nearly identical mix of elements. A handful of candidates have been proposed. None have been confirmed with certainty. The Sun's original family is gone, unidentifiable, dissolved into the general stellar population of the galaxy after 4.5 billion years of orbital drift. Every star you can name in the night sky, every star inside the 200 sextillion total, went through some version of this same process. A cold cloud, a slow collapse, a burst of birth alongside hundreds of unseen siblings, and eventually, a long drift into anonymity within the wider galaxy. The count doesn't just have to reach across space. It has to reach across every stage of a process that, for any individual star, takes millions of years to complete. Not every cluster falls apart quickly, though. Globular clusters, the same ancient, tightly packed spheres of population 2 stars mentioned earlier, are a striking exception. Unlike open clusters, which typically hold together for only a few 100 million years before the galaxy's tidal forces pull them apart, globular clusters can remain gravitationally bound for over 10 billion years. The difference comes down to sheer density. A globular cluster can pack hundreds of thousands of stars into a region just a few dozen light-years across, so tightly bound by their own combined gravity that the galaxy's outer tidal pull struggles to break them apart. Some of the globular clusters orbiting the Milky Way today are nearly as old as the universe itself. Ancient survivors from an era when the galaxy was still assembling out of smaller pieces. They are, in a sense, fossil star clusters, frozen relics of star formation events that happened before the Sun, before the Milky Way's spiral arms, before almost everything else described tonight had taken shape. That contrast, a young open cluster like the Pleiades, scattering within a few 100 million years, against a globular cluster still intact after more than 10 billion, says something about how differently the universe holds onto the stars it makes, depending on nothing more than how tightly they happened to form together in the first place. Let's talk about what lives around those stars. Because this is where the star count intersects with something that changes how you think about each individual star as a number. For most of the 20th century, we didn't know whether other stars had planets. We assumed they probably did. But we couldn't prove it. The first confirmed detection of planets orbiting a Sun-like star came in 1995, when Swiss astronomers Michel Mayor and Didier Queloz announced the discovery of a planet orbiting 51 Pegasi. It was a Jupiter-sized world orbiting its star in just 4 days, a hot Jupiter close to its star. Nothing like our solar system. Mayor and Queloz won the Nobel Prize in Physics for this discovery in 2019. After 51 Pegasi b, planet discoveries accelerated. Then the Kepler Space Telescope launched in 2009 and transformed everything. Kepler stared at 145,000 stars for 4 years, measuring their brightness with extraordinary precision, looking for the tiny dips in brightness that occur when a planet crosses in front of its star. The results were decisive. Planets are not rare. They are common, extraordinarily common. Statistical analysis of Kepler's data suggests that, on average, every star in the Milky Way has at least one planet, possibly more. The estimate now stands at somewhere between 1 and 2 planets per star, on average, with many stars having multiple planets. Some stars have systems of 5, 6, 7, or more planets, like TRAPPIST-1, a red dwarf 40 light-years from Earth with at least 7 planets, 3 of which orbit in the habitable zone where liquid water could exist on a rocky surface. Proxima Centauri, the closest star of all, has its own confirmed planet, Proxima b. Discovered in 2016, it's roughly Earth-sized, orbiting within Proxima Centauri's habitable zone, close enough that liquid water could theoretically exist on its surface. But being close to a red dwarf carries a cost. Red dwarfs, despite being cool and dim, are prone to violent flares, sudden bursts of radiation far more intense relative to their size than anything the Sun produces. A planet orbiting close enough to stay warm is also close enough to be regularly blasted by that radiation, which may strip away atmospheres over time. Whether Proxima b could actually support anything resembling life remains an open question, and one of the most actively studied in modern astronomy. The TRAPPIST-1 system raises the same question on a larger scale. 7 Earth-sized planets, tightly packed around a single red dwarf, 3 sitting in the zone where surface water could exist. If even one of those 7 turns out to be genuinely habitable, it would mean that a single ordinary red dwarf, one of 200 sextillion stars scattered across the observable universe, is quietly hosting a second chance at life within our own galactic backyard. If every star has at least one planet, and there are 200 sextillion stars in the observable universe, then there are at least 200 sextillion planets. The universe is not mostly empty. It is filled with worlds. Worlds we cannot reach. Worlds we cannot see directly. Worlds that may be barren or may not be. We don't know. Every star in the sky might have a planet. Every one of those 200 sextillion points of light is a sun, and almost every one of those suns may have worlds of its own. Stars rarely form completely alone. They're usually born in clusters, groups of stars that condensed out of the same collapsing cloud of gas and dust at roughly the same time. Two broad types of clusters exist, and they tell very different stories. Open clusters are loose young groupings, typically containing anywhere from a few dozen to a few thousand stars, spread across a region a few dozen light-years wide. The Pleiades, visible to the naked eye in the constellation Taurus, is an open cluster containing around 1,000 stars, though only a handful are bright enough to see without a telescope. Open clusters don't stay together forever. The gravity of the galaxy itself, along with close encounters with other stars and gas clouds, gradually pulls them apart. Most open clusters disperse within a few 100 million years, their stars scattering to become the ordinary, unclustered population that fills most of a galaxy's disk. The Sun itself, likely formed in an open cluster of this kind, alongside thousands of sibling stars that have long since drifted away, scattered across the galaxy, impossible to identify individually anymore. Globular clusters are a different phenomenon entirely. These are old, extremely dense, roughly spherical swarms, often containing hundreds of thousands of stars, sometimes more than 1 million, tightly bound by gravity into a region only a few dozen light-years across. The Milky Way hosts around 150 known globular clusters, orbiting the galactic center in wide, looping paths that carry them far above and below the galaxy's disk. Unlike open clusters, globular clusters are gravitationally stable enough to survive for billions of years. Many of the stars inside them are among the oldest in the galaxy. Population: 2 stars formed when the Milky Way itself was still assembling. Counting stars inside a globular cluster runs into the same crowding problem described earlier. Dense cores where individual stars blur together, forcing astronomers to estimate total population from integrated brightness rather than a direct tally. Across the whole Milky Way, star clusters, open and globular combined, account for only a small fraction of the galaxy's total stellar population. Most stars, including the Sun, now drift as part of the general disk population, no longer gravitationally bound to the siblings they were born alongside. But every star in that general population once belonged to a cluster. The clusters are simply where the counting has to start, even though most of them have long since dissolved into the wider galaxy. Now, let's zoom out from individual stars and talk about the structures they inhabit. Because stars exist inside galaxies, galaxies collect into groups and clusters, and those clusters are themselves part of superclusters, the largest gravitationally bound structures in the observable universe. The Milky Way belongs to the local group. The local group is a collection of more than 50 galaxies, including the Milky Way, Andromeda, and the Triangulum galaxy, along with dozens of smaller dwarf galaxies. The local group spans about 10 million light-years. The total stellar population of the local group is dominated by the Milky Way and Andromeda. Andromeda, also known as M31, is similar in size to the Milky Way, possibly containing around 1 trillion stars. The local group contains roughly 1.5 trillion stars in total, give or take. The local group is itself falling toward a larger structure, the Virgo cluster. The Virgo cluster is a cluster of more than 1,300 galaxies located about 50 million light-years from Earth. It contains some of the largest galaxies known, including Messier 87, an elliptical galaxy at the cluster's center with an estimated 6 trillion stars. 6 trillion. That's 6,000 billion stars in one galaxy, 24 times more than the Milky Way. Messier 87 is also the galaxy at the center, of which, in 2019, we captured the first direct image of a black hole's shadow. A black hole, with a mass 6.5 billion times the mass of the Sun, surrounded by a glowing ring of superheated gas. In the core of a galaxy with 6 trillion stars. The Virgo cluster is at the center of the Virgo supercluster, which is itself a smaller structure within an even larger one. In 2014, a team of astronomers, led by Brent Tully, mapped the motions of thousands of galaxies across a vast region of space, tracing the gravitational flows of those galaxies to identify their supercluster boundaries. What they found was Laniakea, a supercluster spanning 500 million light-years, containing roughly 100,000 galaxies, with a total mass of about 100 million billion times the mass of the Sun. Our local group sits at the edge of Laniakea, the Milky Way, on the outer fringe of a supercluster containing 100,000 galaxies. Laniakea is itself embedded in the cosmic web, the large-scale structure of the universe. The cosmic web looks like a three-dimensional network of filaments and nodes. Filaments are long strands of galaxies and gas connecting the dense nodes. The nodes are galaxy clusters and superclusters. Between the filaments and nodes are the voids, vast regions of space, largely empty of galaxies. The Botez void is one of the largest known. It spans roughly 330 million light-years. If you lived in a galaxy in the center of the Botez void, your nearest galactic neighbor would be 100 million light-years away. You would look in every direction and see almost nothing, no neighboring galaxies, just darkness, extending 100 million light-years in every direction. It would take humanity several more decades of technological advancement just to detect that other galaxies existed at all. The cosmic web is the largest confirmed structure in the observable universe. And every filament, every node, every galaxy in that web contains stars. 200 sextillion of them, at minimum. Let me tell you about the history of counting. Because humans have been trying to enumerate the stars for a very long time. The ancient Greeks made careful catalogues. Hipparchus, in the 2nd century BC, catalogued about 850 stars by position and brightness. Ptolemy expanded the catalogue to about 1,020 stars. These were the stars you could see. Nobody had any conception of how far away they were, or what they were. They were lights in the sky, believed by many to be holes in a celestial sphere, with fire shining through from beyond. Then came telescopes. In 1609, Galileo turned a simple spyglass toward the Milky Way and discovered something that changed astronomy forever. What looked to the naked eye like a glowing band of light dissolved, through the telescope, into thousands of individual stars. Stars so close together they couldn't be resolved with the naked eye. Stars so numerous that no one had suspected they were there. That single observation established that the Milky Way was made of stars, not fog. But how many stars, and how large the structure containing them, remained deeply uncertain. William Herschel, in the late 18th century, made the first systematic attempt to map the Milky Way by counting stars in different directions. He assumed all stars were approximately the same intrinsic brightness, then used relative brightness as a proxy for distance. Brighter stars were closer. Dimmer stars were farther. By counting how many stars he could see in different directions and how bright they appeared, he tried to infer the three-dimensional shape of the Milky Way. He correctly deduced a disk shape, but placed the Sun near the center, which turned out to be wrong. His method failed because he couldn't account for the dust clouds that block light in certain directions, making the Milky Way appear smaller and the Sun more central than it actually is. It wasn't until the early 20th century and the work of Harlow Shapley that the Sun's true position was established. Shapley studied globular clusters, those tight balls of ancient stars orbiting the Milky Way. He found that they weren't distributed randomly around the sky. They were concentrated in one direction, the direction of Sagittarius. Shapley correctly deduced that the center of the Milky Way was in that direction, far from the Sun. We're not at the center. We're in the suburbs. This was a significant humiliation. Not the last one astronomy would deliver. Then came the question of whether our galaxy was the universe. In the early 20th century, the debate was genuine and fierce. Some astronomers believed the Milky Way was the entirety of creation, with the small fuzzy patches called nebulae being small objects within our galaxy. Others believed those nebulae might be island universes, separate galaxies like our own, at unimaginable distances. The debate was settled in 1924. Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory in California, resolved individual stars in the Andromeda Nebula. Among them, he identified a Cepheid variable star, a type of star whose intrinsic brightness is directly related to how fast it pulses in and out. This relationship had been discovered by Henrietta Swan Leavitt in 1912. Leavitt was working as a human computer at the Harvard College Observatory, assigned to measure and catalog the brightness of stars on photographic plates. She noticed that in the small Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, the Cepheid variable stars followed a pattern. The ones that pulsed more slowly were intrinsically brighter. The relationship was tight, predictable. If you knew how fast a Cepheid pulsed, you knew how bright it actually was. Compare that to how bright it appeared from Earth, and you could calculate the distance. Cepheids became the universe's first reliable distance markers. Standard candles, objects of known luminosity that you could use to measure distances to other galaxies. Hubble used Leavitt's work. He measured the pulsation period of the Cepheid in Andromeda, calculated its intrinsic brightness, compared it to its apparent brightness, and derived a distance. Andromeda was nearly 1 million light-years away, far outside the Milky Way, later revised to 2.5 million light-years. Either way, it was clearly not part of our galaxy. The Andromeda Nebula was an island universe, a separate galaxy of stars so distant that its individual members had been invisible to all previous observation. The universe had just gotten unimaginably larger, and the number of stars within it had grown by a corresponding amount. The chain of discovery didn't stop there. In 1929, Hubble announced another discovery. This one, even more disorienting. Galaxies are moving away from us. All of them. The more distant the galaxy, the faster it recedes. This wasn't because galaxies were flying through space away from us. It was because space itself was expanding. The universe was not static, it was expanding, and had been since the beginning. The implications were immediately obvious. If the universe is expanding now, then in the past it was smaller. If you run the expansion backward in time, eventually you reach a point where all the matter and energy in the universe was compressed into an extraordinarily small, hot, dense state. The Big Bang, 13.8 billion years ago. The observable universe has a finite size because it has a finite age. Light can only have traveled so far in 13.8 billion years. Beyond that distance, we can't see. The observable universe isn't the entire universe. It's just the portion that's close enough for light to have reached us. The actual universe, beyond our observational horizon, may be vastly larger, possibly infinite. If the universe truly is infinite, the implications for a star count are strange enough to sit uncomfortably with the rest of tonight's numbers. An infinite universe, filled with matter at roughly the density we observe nearby, wouldn't just contain more stars than 200 sextillion. It would contain infinitely many, and mathematically, infinite quantities don't behave the way large finite ones do. Some cosmologists have taken this further, arguing that an infinite universe with roughly uniform physical laws would, somewhere within it, repeat every possible arrangement of matter, simply because there are only so many ways to arrange a finite number of particles inside any given region, and an infinite universe has room to try every arrangement more than once. This isn't a mainstream, settled claim, since it can't currently be tested. It's a mathematical consequence of taking infinity seriously, one that most cosmologists treat as a curiosity rather than a genuine prediction. But what lies beyond our horizon is, by definition, inaccessible to observation. We can't count the stars out there. We can't even know whether our extrapolations apply. The 200 sextillion number is strictly a count for the observable universe. The universe as a whole, if infinite, contains infinitely more. The history of counting didn't stop with Hubble. In December of 2013, the European Space Agency launched a satellite called Gaia, and it changed what precise counting actually means. Gaia's job wasn't to look far away. It was built to measure, with extraordinary precision, the exact position, distance, and motion of over 1 billion individual stars in the Milky Way. Not estimate. Measure. Star by star. Gaia does this using a technique called parallax, watching how a nearby star appears to shift slightly against the background of more distant stars as Earth orbits the Sun. That tiny shift, measured with almost impossible precision from a spacecraft orbiting nearly 1 million miles from Earth, gives a direct geometric distance, no assumptions about brightness required. Before Gaia, distances to most stars were estimated indirectly, using brightness and spectral type as a proxy, an inference method not unlike the ones used to estimate galaxy counts. Gaia replaced inference with direct measurement for over 1 billion stars, producing the most precise three-dimensional map of our galaxy ever made. 1 billion stars sounds enormous, until you remember that the Milky Way alone likely contains somewhere between 200 and 400 billion. Gaia has mapped less than 1% of the galaxy's total stellar population, and that 1% required one of the most ambitious space missions ever flown. That ratio says everything about the scale of the problem. If measuring 1 billion stars precisely, one at a time, from one galaxy, is considered